before we begin, let's just go back and let me remind you what we covered in the last lecture. So first of all, I talked to you about how to, about the physical mechanism to do quantum nonlinear optics based on strongly interacting atoms. And the second thing is that I discussed EIT that we sort of use as a tool to kind of actually do these experiments, to take advantage of this strong nonlinearity induced by atom-atom interactions. And one of the things which I actually left for you to do is to do the homework. So should I ask for the homework solution, or is it sort of too much to ask? So what's the adiabatistic idea? Do you remember? What's the condition for adiabatic passage? Yeah?
The chi square n is bigger than the decay rate, is contains decay rate.
Well, okay. So this is already sort of as a consequence of the well, that cannot be quite right. So there should be a time scale, right? If we do, for a single atom, if we want to do adiabatic passage, right? If we do slowly enough, then the transfer will be adiabatic, right? And basically, the condition which ends up being here is basically that this kind of radio frequency, the sum of radio frequencies, if you want, is actually sufficiently large that basically so this times t is much larger than 1. So that's the adiabatic condition. Right? So if time is very long and the radio frequency is very strong, so this is, if this condition is fulfilled, then and that's what we're supposed to derive, but somehow maybe it's already too late to kind of enforce my exercise. So okay, so I will forgive you this one, but I think this is really a good exercise. And actually, for example, you can look in the lecture notes which I quoted if you want to see how this can be done in a kind of simple and intuitive way. All right, so what I'd like to do now is to basically go back to the discussion, and since it's quite late in the evening, I will actually try to sort of simplify things a little bit. Will be a lecture light and maybe tell you a little bit more about the experimental results. But actually, there is one thing that there is one piece of business that we have to do, and this is a fifth thing that you need to know. So basically, I started talking about this, the experiments which we are doing, where we basically, in an ensemble of cold atoms, send in the weak probe light, which is resonant with this kind of optical transition, and then we drive the AIT by using the blue light to excite this kind of AIT in the infrared states. And basically what I've showed you, I concluded my discussion by showing you this view graph where we basically see some very rapid saturation, where just if the photon flux exceeds just few photons per microsecond, we see how pretty nice AIT all of a sudden goes away. But the question that we would like to ask now is there any kind of quantum signatures in this AIT process? In particular, can we see the signatures of single photons interacting with each other? So in other words, is it a quantum nonlinearity, or is it just a classical average kind of nonlinear effect? And in order to answer that, we need this last fifth thing that that you must know before you leave. So, did you at least have some, did you at least thought about that? So what is the fifth thing that we need to know?
photon statistics?
Exactly. So that's very much related to the issue of photon statistics. In particular, very appropriately with Roy sitting in the audience, the thing that you need to know is basically coherent and non-classical states of light. So basically, up to now, most of our discussion was focused on just using classical light. Like the classical light meaning that we can describe this light using Maxwell's equations, using Wave's equation. So, is it always possible to describe light in this way or not? And under what conditions can you use Maxwell's equations to describe the physics? Right? That's what basically, Roy, sort of the theory that Roy outlined a number of years ago tells us. So, and the best way to kind of approach this problem is to first try to understand what is the quantum state which kind of approximates the classical light. Right? What will be a quantum state that you need to, light fundamentally is a quantum object, right? So, but what is the quantum state which will best approximate the classical description of light? And so you sort of know how to approach that. So basically, if you quantize the light, then each mode corresponds to what? Just to a simple harmonic oscillator, right? And then basically each mode of light, so it can be described by a Hamiltonian, which is essentially a frequency of this mode, times this harmonic oscillator Hamiltonian, where the Geiger is harmonic oscillator creation and annihilation operator, right? And so basically the electric field and the electric field operator can be written basically like this, where, for example, for any wave, it can be written in terms of this creation and annihilation operator in this kind of form. And so the electric field is actually proportional to some kind of combination of creation and annihilation operator. And now, of course, if you want to really go back to the classical theory and want to really treat this operator as a C number, kind of the most sort of intuitive way would be to try to replace this and this guy by C numbers, right? And that's kind of a motivation to define the so-called coherent states. So the coherent state is a state which is basically an eigenstate of the annihilation operator. And so if you can do this kind of stuff, right, then essentially, you can basically replace the electric field operator with a C number, right? And the C number will have well-defined amplitude or seemingly well-defined amplitude and phase, and then, classical description is appropriate, right? So that's sort of the end of the story, is it? So what is the kind of quantum feature in this kind of classical type system that you can observe, like in a coherent state? What is a quantum feature which you can observe in a coherent state? Sometimes it's called quantum noise.
Spontaneous emission.
What?
Spontaneous emission.
Nah, we are not really talking about spontaneous emission of fields if you start talking about fields interacting with atoms. At this point, we are talking about free fields. So what is there anything, like if you attack the field in a coherent state, right? Is there any kind of feature or measurable quantity which you can come up with, which will actually tell us that it is actually a quantum state and not just classical C number? What? What?
Number of photons.
So what about it? So yeah, let's think a little bit about number of photons. So what's the number of photons, by the way? So if you look at the number of photons, it is described by an operator, which is A divided by A, right? And so what's the number of photons in a coherent state? Or let's say, what's the average number of photons in a coherent state? Yeah?
Square root of alpha.
It's square of alpha, right? So indeed, so if you just take the expectation value of this, right, this operator on the right acts on alpha, right, and A dagger acts on the bra, right, and so this is just alpha squared, right? So that's average. So is there anything quantum about this photon number? Is there any kind of trace of quantumness? And if so, what it is? So sometimes this stuff is called quantum noise, kind of loosely speaking. What is quantum noise?
Fluctuation in the number of photons?
Exactly, it corresponds to fluctuations. So this is an average quantity which we found. Note, however, that the coherent state is not an eigenstate of the number operator. Right? So as a matter of fact, if you calculate the variance of what a number operator, for example, a quantity which you can define as something like n minus n squared, right? So if you calculate the variance of this, the average of this variance, what will you get? Anyone knows?
Square root of
Is it the square root of n? Is it?
It's just n.
It's just n, right? It's because I'm looking at square, right? If I take a root, so it's just n. So, okay, so the reason is that the coherent state is not an eigenstate of the photon number operator, right? Why is it not? Kind of in terms of a physical picture, right? So the coherent state has a well-defined phase. And if something has well-defined phase, right, it cannot have a well-defined photon number. So indeed, this is the case, and in fact, what you can do is you can actually write coherent state in terms of, as a kind of superposition, you can expand it in terms of the photon number operator. So in fact, the expansion looks like this. And so what you see is that, basically from here you can, for example, see that the photon number distribution in this coherent state will be, will basically correspond to a Poissonian distribution. So in other words, if you take this state and make a measurement on the photon number multiple times, right, you'll get slightly different results, right? On the average, this will, on the average, you will find that you have this kind of alpha squared photons, right? But from shot to shot, you will have some fluctuations in this measurement. And these fluctuations will have variance, which will be basically given by n, right? So this coherent state has a well-defined phase, so consequently it will have fluctuation in number of photons. Yeah. So that's a classical state. But you know, the coherent state is the best possible kind of quantum approximation to the classical state. So coherent state is something you really have to know if you want to kind of do anything which is related to quantum optics. This is one basic concept that you really must know. Are there any questions about it? So, is there anyone who has not heard about coherent states previously? So then how come that you guys don't know about the variances? Okay, so these are the things which you have to know. So now, let me ask you another question. So, when people talk about, you know, sort of when you go to conferences and talk about non-classical states. So what is non-classical state? So what do they mean by that? Is a coherent state non-classical state?
The number distribution is somehow not Bosonian.
Okay, so is it really all of the criteria? Because, you know, it's true that, you know, there are some states, indeed there are some states, for example, the state is well-defined photons, right? The Fock state, this is actually a non-classical state, right? So this is a state which which has which an eigenstate of photon number operator, it does not have phase defined. So it's an example of non-classical state, right? So it's different, kind of a different class from the coherent state, right? So it's one example, but you know there are other examples, right? For instance, there are the so-called squeeze states, right? So states which have variance in one of the kind of quadrature component, like X or P of the harmonic oscillator, which is actually squeezed compared to the coherent state. So in the coherent state, X and P are also not well defined, right? They have an uncertainty. These uncertainties are the same in some kind of normalized units, and they minimize the uncertainty relation. Right? But basically, there are some states which you know, X, for example, can be much smaller than P, when both their product is, you know, kind of consistent with uncertainty relation. So basically, these are different, all different examples of non-classical states. So in general, non-classical states can be thought of as states which cannot be represented as a kind of statistical mixture of different coherent states. Right? So coherent states is basically kind of a classical, it's a classical, essentially classical state, right? And basically, if you can sort of have if you can have a state like a thermal state, for example, you can think about it as a statistical mixture of different coherent states. It's still kind of classical, right? Even though it doesn't have Poissonian statistics, actually has super Poissonian statistics, but still, if you take a lamp, you can, you know, filter a lamp with some filter, you can create this kind of state. Now, let me ask another question. What about the states which are coherent superpositions of the of two or more of coherent states? Are they classical or non-classical?
They all have different phases, right?
Yeah. Are these classical states?
I wouldn't say that they are.
Yeah, so it is. So indeed, for example, if you take a state which is a state like this, so this is a highly non-classical state. For alpha equals large, this is actually a Schrödinger cat state. So this is a state where basically just superposition of two distinct macroscopic states, right? In fact, coherent states are actually complete, they're actually over-complete. So in principle, any state can be represented as a superposition over the coherent states, right? So, so these are two examples of non-classical states. The Fock states, these are the Schrödinger cat states. So now the last question which I would like to ask, which sort of requires concentration, how do you call it, that requires your attention span to be focused before the entertainment starts. Is the following. So how can I distinguish the so-called classical states from non-classical states? How can I actually quantify, for example, how can I experimentally measure that the state which I created is not the one which is described by Maxwell's equations?
By looking at the photon statistics, what is that question?
So what does it mean measuring kind of photon statistics?
Looking at the variance.
What?
Looking at the variance.
Exactly. So what I need to do is, instead of measuring average quantities, for example, measuring average amplitude of electric field or measuring average photon number, I need to look at fluctuations. Right? So basically, to measure non-classical states, you need to look at fluctuations. So in other words, you have to basically look at noise, right? So, for example, in the case of coherent state, if you measure photon number, right, what you will find is that the photon number is uncertain, right? So if you, for example, would like to distinguish Fock state from coherent state, what you need to do, you need to measure the fluctuation in a photon number. Right? So how can one do that? What are the ways how to do it? Any suggestions?
You mean experimentally?
Experimentally, yeah.
Hanbury Brown-Twiss interferometer.
Well, so one example is the so-called Hanbury Brown-Twiss. So actually I'm going to discuss it now in some details. So basically the idea here is the following. So you take your beam of light where you would like to measure the statistics, and you put a beam splitter. Basically you split it on a beam splitter and put two detectors. Right? And basically what you do then, you look at coincidences of these detectors. Right? So that's a method which I'm going to employ. But let me take a step back and ask, so why can't you do this directly? So why can't you just take a light pulse and send it on a photodetector and just count how many photons this pulse contains? Why go through this trouble? Yeah.
There's some finite efficiency in the detector.
That's one reason, right? But in this case, there are also some finite efficiency, of course. But it affects differently different measurement techniques. But there is another reason why at least sort of conventional APDs, you cannot use conventional APDs to do it. What is it?
They have at that time.
That's right. So basically, conventional APDs, they can count single photons with reasonable efficiency, sometimes 60, 70%. But for example, if two photons come very close together, right? Conventional APD will not be able to distinguish one click from two. And because they work on a principle of avalanche, so when one photon comes, it causes an avalanche, which exists for a certain finite amount of time. And during this avalanche, if the second photon comes, then the detector will not respond. Right? So these detectors can distinguish 0 clicks from 1 click very well, but they will have trouble distinguishing 1 from 2. So there are now different types of detectors, like superconducting detectors, which actually can distinguish that. In these cases, you can actually try to do it. Of course, there is a problem also of the efficiency, but nevertheless, that's actually the reason. So the so-called Hanbury Brown-Twiss setup, where you do this kind of things and look for coincidences. Is a method of choice for many situations where you would like to, for example, distinguish single photon states from the coherent state. And basically, following Roy's work, in 1960s, what one often does, one quantifies the signal that you measure in terms of basically essentially coincidence probability as a function of the separation between detection events. And this can be quantified by this so-called G2 function, which one can write basically as something like this: A of 0, A of tau, and this is normalized by something like this. So let's kind of illustrate a little bit, how this works. So let's, for example, take the single photon state with n equals 1, right? So let's develop an intuition, right? So what happens here is if there is one photon in a Fock state, which will come to this beam splitter, right? And then it splits into two paths. So what will be the probability of coincidence in this case? What?
If it's a one photon, it can split at 0.
Exactly. So one photon will either go this way or will go this way. You don't know, it's statistical, right? But in this case, there will be never a coincidence. I mean, if you take this kind of one photon, substitute it here, it's basically annihilated immediately by the first operator, so the numerator will be 0. So consequently, this G2 here will be 0. It's very different from the coherent state. Right? So if you start in a coherent state, what will be G2? 1. Why is that? So mathematically and physically. Let's try to understand it both mathematically and physically. Yeah?
Mathematically, if you apply the annihilation operator, it's just the same.
Exactly. So this coherent state is an eigenstate of annihilation operator, right? So basically what this means is that for this normally ordered operator, I can just replace A by C number, right? That's why it's classical, right? So classical, just replace an operator by C number, and we can do it here. And this indeed, in this case, will be G2 will be equal to 1, right? So that's mathematically. So physically, why is it non-zero? So physically, what will happen, right? So physically, what will happen is that, yeah?
It's the classical picture of light is like a wave, which can be split on a beam splitter.
Exactly. Exactly. So this beam splitter is a linear optical element, and so by definition, it takes a coherent state and converts it into two different coherent states, right? Which just go into this intensity, which is half, to preserve the energy, right? And once these coherent states hit these detectors, this will occur totally at random, and of course there will be some coincidences, right? So that's a physical picture. Okay, so that's a little bit of the introduction to this point number 5. So basically, if you want to do work in quantum optics, this is one of the fundamental things that you need to know. Are there any questions about this? Yeah?
Having a G2 of 0 doesn't necessarily give you a Fock state with n equals 1, right? You could also have always n equals 0.
Well, so when n equals 0, right, this quantity is technically not defined, right? Because both numerator and denominator is 0. Right? But what is true is that kind of in practice, and for example, in the cases when I will be talking about here, so we seldom really produce a truly Fock state. So most of the states which are produced are states like this. They are mostly vacuum, plus with a little bit, some small probability you have a Fock state, right? So for example, if you have a single photon emitter, if you excite it, right, by the time this excitation tickles down to the detector, right, it will be absorbed or scattered with some probability, right? But nevertheless, G2 will be equal to 0 if it's a single photon emitter, right? And so the reason is that the state like this will also have G2 equals 0, right? So in this case, what this Hanbury Brown-Twiss really measures is the relative weight of a single photon component and a two photon component, right? So that's, that's a very, very good. But nevertheless, in all cases, this is a non-classical state, right? So this state is not a classical state because it has no two photon component. Any other questions? All right, so this concludes these 5 things that you need to know. And if you think back about these 5 things, for example, just last 10 years, count the Nobel Prizes, which were sort of awarded for key insights combining these 5 things. There is a fair number, right? And this is not the end of the story. So these are really, really important fundamental things. All right, okay, so now let's go on and see how this, how this really applies to the story that I'm trying to tell. So essentially, what we can do now is go back to this kind of experimental setup and look for quantum statistics of the light which goes through this kind of atomic ensemble, right? And what we can do in the simplest way is just we can put this beam splitter here and just look for coincidences. Okay? So this can maybe help us to distinguish classical nonlinearity from the quantum nonlinearity. So here is what comes out from this measurement. So if we measure G2, then what we observe, indeed, that when tau is very small, what we observe is that G2 is much, much smaller than 1. Right? So what does it tell us? It tells us that in such a medium, if we send the coherent light, right, and drive these polaritons to the state with n equals 100, this medium does not allow two photons to basically propagate together, right? It's very much consistent with what we have expected, right? Because basically we cannot have EIT for two photons which are sitting on the top of each other. So, and this is very much due to the Rydberg interaction, because if we go to lower state, for example, n equals 46, then G2 is equal to 1, or close to 1, which is basically consistent with G2 of the laser beam, right? So this non-classical feature here appears only when we go to the Rydberg state with sufficiently large interaction. Now, okay, these are good news. So what we see is only one photon at a time is transmitted for high n. But then there is another thing which we can check. So I will just take a question in a second. So another thing which we can check, is our sort of expectation that this kind of Rydberg blockade is the right kind of length scale, right? And what we can, the way how we can check is basically we can just look at this time scale and we scale it with the group velocity, and this gives us a length scale. And actually, somewhat surprisingly, at least at the time for us, we found that this correlation length, the length over which the photons can really feel each other, is actually much larger than the Rydberg blockade. So the Rydberg blockade radius here is maybe 10 micrometers, but what we see is that basically our correlation length is about 50 micrometers. It's about equal to the size of the cloud. So what this really means is that, in a case like this, two photons cannot be at the same time in a cloud. Okay? So there's a question.
No. Can you explain again what does it mean, the correlation function bigger than 1?
So correlation function bigger than 1 means that you have kind of more fluctuations compared to do Poissonian light. That means it's kind of some kind of Poissonian statistics, right? And then maybe one question that you can ask is that, wait a second, so what are you showing me here? So you're showing that this here is fluctuations are suppressed, right? But then instead of going to 1, this G2 goes to 1.2, right? First of all, can this be the case, and how? If so, how? And actually, if you go back to this definition of G2, then there is one conclusion which you actually make by so-called method of careful, how to translate it from Russian, viewing, careful inspection, right? So one thing is that, if tau goes to infinity, right, if the time separation goes to infinity, what should be the value of G2? Should be 1, right? Because when tau goes to infinity, you're basically looking at completely two uncorrelated processes, right? For one detector and for another. So these things totally should be uncorrelated, right? And consequently, G2 should be equals to 1. So what this means is that for the plot like this, when tau goes to infinity, or to a very long time, this G2 should eventually come down to 1, and in fact it does. So that's one observation. The second observation, why does it go up here, right? And so when the G2 goes up, it kind of suggests that you basically have some extra additional kind of source of noise. And it's actually related to some of the discussions which already took place, I believe, during the other talk. So we believe we actually understand why this happens. And this is due to this noise, is basically due to the following. So we have this kind of extremely nonlinear medium where one Rydberg atom can block the transition of all photons, right? So, and what happens here is that basically when we excite this Rydberg atom, then the first photon